Nearly a century ago, Dr. Arnold Beckman transformed science by solving simple but critical problem: how to measure acidity reliably. His invention of the first modern pH meter made it possible to quantify chemical behavior, thus opening the door to major advances in fields from medicine to environmental science. He went on to create other groundbreaking instruments that made invisible chemical processes measurable and predictable, giving scientists entirely new ways to understand how complex systems work. Hi, my name is Jaehyeok Jin, and I'm a 2022 Arnold O. Beckman Postdoctoral in Chemical Sciences. My research follows the same spirit that defined Dr. Beckman's career. He built tools that allow scientists to see chemistry more clearly. Following the same inspiration, I built theoretical and computational tools that allow us to make accurate predictions about the chemistry. A simple example is the battery inside your cell phone. When you charge and recharge the battery, tiny needle-like structures called dendrites can grow inside. These dendrites can reduce performances and even cause failure. What we still don't fully understand is how the motion of individual molecules deep inside a battery influences the shape, growth, and stability of these dendrites at much larger scales. To address this, we need tools that can connect what molecules do at the tiniest scales to the behavior we see at the human scale. In my fellowship, I developed a new class of multi-scale models that connects the invisible world of atoms to the visible structures and behaviors we observe in materials using computer simulations. Currently, computer simulations allow us to efficiently investigate molecular mechanisms of complex chemical systems that are difficult to characterize experimentally. However, these simulations typically remain at the molecular level, meaning that they struggle to predict very large-scale or long-time-scale processes that matter for real materials. My postdoctoral research takes a bottom-up approach, meaning that starting from the well-established motions and interactions of atoms, then simplifying them into molecular models, and finally building up to continuum-level descriptions that capture the behavior of entire materials. This approach allows us to faithfully preserve the underlying physics at each scale while still being able to predict processes that occur over much larger distances and over long times. Using tools from physical chemistry, so statistical mechanics, continuum modeling, and coarse-graining theory, and with the support of the fellowship, I was able to show how we can predict important processes that were previously very difficult to model. At the molecular level, I bridged quantum mechanics to molecular coarse-grain level for proton transport phenomena to capture reactive processes with much accelerated computational costs for aqueous and confined environments. I also developed new molecular coarse-graining theory that can be transferred to multiple configurations in complex systems, such as polymers or proteins, where they have folded and unfolded conformations. Beyond the molecular level, I published a series of papers on mapping complex molecules to simple, analytic, Hard-sphere descriptions, and thus capture the complex dynamics and thermodynamic properties at the atomistic level with predictable theories. Using this idea, I developed a new theory of coarse-graining in space and time beyond conventional coarse-graining approaches that allows for predicting transport properties of glass-forming liquids at very low temperatures. I continued these bottom-up approaches at continuum level, where I devised a rigorous approach to derive fluctuating hydrodynamic descriptions of fluids from realistic molecular description, which opens the door to efficient simulation of realistic fluid systems. Then, I developed a new bottom-up phase field modeling method by incorporating atomistic correlations and interactions into continuum level. This framework was shown for ice crystal growth studies, which really allows for extending the range and accuracy of multi-scale simulation and potentially studying dendrite formation in energy storage materials. These models reveal how microscopic interactions accumulate and produce large-scale phenomena, something we could not previously analyze in a unified and predictive way. Because of these tools, we now have a clearer picture of how molecular behavior shapes the performance and reliability of advanced materials. None of this would have been possible without the support of the Arnold and Mabel Beckman Foundation. This fellowship gave me the freedom to explore building new scientific tools that can really help us to predict complex chemical behavior with clarity and precision. Inspired by Dr. Beckman's vision, my goal is to continue developing rigorous, quantitative approaches that open new windows into chemical and material science. His belief that powerful tools, whether they are physical instruments or computational models, can drive innovation is exactly what motivates my work today.